just to give you guys a little bit more background on who I am, where I come from, why I'm here. So I work for a company called End-to-End Analytics. We are an analytics consulting company based in Palo Alto, California, although we have people all around the world, the Midwest, East Coast, Brazil, Peru, China. We even have people in Europe now. So we are everywhere, and we work with companies of all different industries and every type of analytics. Descriptive, predictive, prescriptive, you name the type of analytics, we do it. Although our bread and butter really is operations research problems, and we end up working with a lot of companies' supply chain groups. So we help companies to optimize and streamline their supply chain processes. I think our magic in doing so, our secret sauce, is really our ability to combine consulting, analytics, and technology in a way that provides actionable solutions for companies. And we do that by building custom tools for everyone we work with. So everyone gets a tailor-made solution specifically for their problem. And we built some pretty cool tools. And last but not least, we have a lot of optimization experts here at End-to-End, and quite a few optimization PhDs. And we are all big fans of Gurobi. Who wouldn't be? We're actually a premier partner of Gurobi, and we have a lot of experience in formulating, modeling, and implementing problems in Gurobi and solving them efficiently and turning that solution into something that you can actually make decisions based on. So we are always happy to help with that. Okay, now to the fun part. So today I'm going to be talking about advanced methods for optimal scheduling. So I gave a webinar a few months ago in July of this year on kind of the beginner tips and tricks for the initial stages of setting up an optimal scheduling model. So if you're interested in that, you can find that recording also on the Gurobi website, although don't hang up on me. You do not have had to listen to that webinar for this one to be relevant. So it really is just a matter of where you are in the stages of setting up your model. This one is definitely on some more advanced methods, and I'm going to focus on how to solve a problem efficiently. So I'm going to start by giving a very quick overview of what scheduling problems are. And then I'm going to introduce a sample problem. And through that sample problem, I'll show how we can formulate the model in a few different ways. And we'll see what's the fastest possible way to solve the problem, given a few different formulations. And I'll even show some optimization-based heuristics. And I'm going to introduce a convex nonlinear quadratic constraint. We'll solve that a couple different ways and see what the fastest way to solve it is. I want to emphasize, I will emphasize this again later, this is by no means a benchmarking. This is meant to give you some ideas on if you have an optimal scheduling problem, or really any kind of mix and integer program, and you are trying to solve it efficiently. It's meant to give you some ideas on how to speed up that process. Okay, so what is a scheduling problem? So scheduling problems arise when you want to determine the time periods in which to schedule a series of events to optimize a chosen objective. So the most commonly talked about scheduling problem is the job shop scheduling problem. So if you have a set of jobs and you have a set of machines and you want to assign those jobs to the machines in a way that minimizes the make span. So you minimize the overall amount of time it takes to process all of those jobs in those machines. And you want to find that optimal schedule. So that's a very typical optimization, optimal scheduling problem. If you listen to my previous webinar, I gave the example of a diner, and we had burger makers in the diner where we wanted to figure out when to have the different burger makers working in order to minimize costs. So there are a lot of different applications for scheduling problems, and all scheduling problems can be formulated as a mixed integer program. And a mixed integer program, or a MIP, is an optimization problem with integer and continuous decision variables. And mixed integer programs can oftentimes be solved relatively quickly with an optimization solver like Gurobi. Gurobi is definitely the fastest optimization solver. So if you have an integer program and it's not solving as fast as you would like, you should probably try to plug it into Gurobi. But that's definitely the main challenge with scheduling problems. So when you formulate your problem as a mixed integer program, the main challenge that people have with that is solving the problem efficiently and reasonable time, whatever reasonable time means to you. But that's what we're going to focus on here, is trying to figure out how to solve the problem quicker. Before I go any further, one thing that I think is actually pretty interesting is that the solve time of mixed integer programs does not scale with the number of variables or constraints. So that's a common misconception. I think a lot of times people say, like, I have this many binary variables, how long will it take to solve the problem? And although it is related, it's not always it doesn't always determine how long the problem will take to solve. So I have a table here with some results from Hans Mindelmann's benchmarking. So if you're ever curious, Hans Mindelmann does a lot of benchmarking on optimization solvers. He's kind of the go-to, he is the go-to source for that. And I have his website linked down there, but he does a lot of benchmarking on every type of optimization problem. And you can see on his website that Gurobi is definitely the fastest solver. It's 1.5 times faster than the next fastest, sometimes 5 times faster than other solvers. So definitely the way to go. But these are the solve times for Gurobi on different mixed integer programs. And the rows are sorted decreasing by solve time. And you can see in that top row, a problem that only has 56 binary variables still takes 51 minutes to solve. Whereas in that second to last row, that problem has 63,000 binary variables and it solves in a minute. So the point that this is trying to make is that the solve time of your problem does not always depend on the size. A lot of times it depends on the very specific problem and the characteristics of your problem. If you are trying to solve your problem faster, there are a lot of techniques that we can use, and that's kind of what I'm going to go over, is to give you some ideas for what you can try with your problem. But what is going to make your problem solve as fast as possible may not be what makes my sample problem solve as fast as possible. So it's important to try a number of different techniques, which gives you the fastest runtime. All right. So I'm going to introduce my sample problem, and then we'll go over some of the different options for how we can formulate it. So my sample problem takes place in a cheese production factory. So we have a factory, and in this factory, they have a bunch of different production lines, and they have a few different cheeses that they want to produce on these production lines. And they want to figure out how to minimize the overall cheese making time in this factory. So my cheese factory is called the Cheesemake factory. You can see that's the picture of the factory right there. It's shaped like a cheese, like all cheese factories. All right, so our problem, we have 10 different kinds of cheese, and we have 3 different production lines. And for each different kind of cheese, we have an expected demand that has to be met. So if Gruyere is one of the types of cheese that we have, we might say that today we know that we need 100 units of Gruyere. And we also have a unit production time that depends on each cheese type. So if we say that each unit of Gruyere takes 2 minutes to produce, and we know that we need 100 of them, then we know that overall we need to spend 200 minutes producing Gruyere. All right, so we have 10 different cheeses, 3 different production lines, and we want to assign the cheeses to production lines in a schedule that will minimize the overall time we spend producing the cheese. Now, as you might guess, the Cheesemake factory is known for their efficiency, and they are very insistent on finding an optimal production schedule as fast as possible. So they are a very demanding client, and they really want to make sure that I'm going to find the optimal schedule for their cheese making that finds a solution extremely fast. All right, so I'm confident I can do it. So the first thing I'm going to do is formulate the problem in words. So what we want to do is minimize the overall production time. So we want to minimize the amount of time that we're spending making cheese, subject to 4 constraints. So the first constraint is that we want to make sure we're making enough cheese to meet the demand. That is usually the most important constraint, that we're meeting the demand. So in the case of Gruyere, we want to make sure that we are producing Gruyere for 200 minutes. We want to make sure that the cheese production times are properly accounted for. Again, that loops into meeting the demand. We want to make sure that only 1 cheese is being produced at a time on each production line. So if we are producing Gruyere on time 1, then we can't also be producing Brie on the same line at time 1. And lastly, we want to make sure that each cheese is produced consecutively on a single production line. So if I start producing Gruyere on line 1, for the first 100 time periods, then I can't then switch over to line 2. I want to make sure that everything is on a single line at a time. Okay, so this is our formulation in words. And now we are going to turn it into math. So here, I'm going to formulate the problem using arrays of binary variables. And this is the first way that I'm going to try to formulate, model, and solve the problem. All right, so my main decision variable here is x. And x is going to be a binary variable. And we're going to have an element of x for every production line, every type of cheese, and every time period. So you can imagine that this will produce quite a few binary decision variables. So we have to index over all of those 3 different terms for every binary element to figure out what our schedule is going to be. And that x variable is going to be 1 if GC is being produced on production line P at time T. So that's where we're going to keep track of our schedule. We have another decision variable y, which is also a binary variable. And we're going to have one of those for every production line in cheese. So here we really just want to keep track of which production line we're producing the cheese on. So that variable is going to be 1 if we're producing cheese C on production line P. And lastly, we have our decision variable s, which is going to keep track of our production start time. So this is a common thing that we want to do in scheduling, is figure out when we're starting production. So this is going to be a binary variable for each cheese and each time period. And it's going to be 1 if GC starts production in time T. Okay, and you can see the parameters there on the right. If you want to overanalyze my formulation for my fake problem, please be my guest. Okay, so the first thing we're going to do is we're going to minimize the last production time period. So this variable L here is going to make sure that we are minimizing the time period T for the last production time. So we're going to multiply T times that binary variable X. And anytime X is 1, that means we're producing cheese in that time period. So we're going to minimize that last time period and push that variable down as early as we can go. So we're minimizing the last time period where we're producing cheese. This is going to make sure that we're meeting demand. So for every cheese, that right-hand side there is multiplying our demand by our unit production time. So we're going to sum up for every cheese all the time periods that we're producing cheese and make sure that it is at least as long as that production time that we need. This constraint is going to make sure that we're producing only 1 cheese on a line at a given time. So if we sum up over all the cheeses, and each production line is only producing 1 cheese at a time, at most 1 cheese at a time. These constraints are defining our y variable. So remember, that was to keep track of which production line the cheese was being produced on. So this y variable here is going to be, it's going to be equal to 1 if and only if x is produced on that production line P. So we can do that by setting equal to the max over all time periods of that variable x over all the production lines and cheeses. And then in the second constraint there in that red box, if we make sure that sums to at most 1, then we're making sure that each cheese is only produced on 1 line. And lastly, this variable s is going to be equal to the max of 0 and the production schedule in each period minus the production schedule in the previous period. So you can think about that, or again, you can trust me, and you will figure out that this will give us, this will set the s variable to 1 if and only if we're starting production of cheese in time period T. And we want to sum all those variables for every time period and make sure that they're at most 1, so that we are starting the production of cheese at most once. So this is our initial formulation using arrays of binary variables, and we can solve this problem in Gurobi. So if I use this formulation with 10 cheeses, 3 production lines, and an average of 7 production time periods per cheese. So that means on average, if we take each cheese and the number of time periods it takes to produce a unit of cheese times the demand, I'm saying that on average, if we say it takes 7 minutes to produce all the cheese we need over all the cheeses, then we're going to have this many variables. And remember, the time periods are important because we're actually indexing over the time periods. So the longer our time horizon is, the more binary variables we have. So the time periods does come into play into how many binaries we have. So if we formulate this problem in Gurobi, we end up getting 650 decision variables, 400 binary variables, and 710 constraints. So even for this small sample problem, we still end up getting a decently large problem. So I solved this problem, and because I didn't have real data, I made up data and I randomly generated 30 different data sets for this model. And I plugged those data sets into the model in Gurobi and solved it. So you can see here that plot on the right, the light blue is the range of solve times that it took as I tried to solve the problem for different problem sizes. So you can see that as we have more cheeses and more lines, the problem, more production lines, the problem does take longer to solve as we increase, right, which is intuitive. And that dark blue line shows the mean. So on average, over this range of 30 problems that I tried, on average, how long does it take the problem to solve? So in this range, for the different data sets I generated, it takes from anywhere from 30 seconds to 3 minutes to solve. And again, this really shows that it really depends on the data. So even given the same exact formulation and the same exact model, if we plug different data in, it can solve in 30 seconds or it can solve in 3 minutes. And that's a huge difference, right, for a small problem. So I want to emphasize again, and this is not a benchmarking, I was running this on my MacBook, it's a few years old, while I was making the slides. So don't take this as Bible of how long it will take to solve a problem. This is more to give you a sense of how it increases over time, right? So if the bigger the problem is, the longer it takes to solve, and there is always still a range of how long the solve time is. All right, so I talked to the cheesemake factory and I formulated their problem and I solved it and I got a solution, and I'm gonna say I can get you a solution in a minute and a half, right? About a minute. It's gonna be pretty good. I'm sure they're gonna be happy with that. So I'm gonna talk to the cheese factory and I communicate with cheesemake factory like I communicate with all of my clients over text message in all lowercase. It's very professional. So my main contact over at the cheesemake factory is someone named George. So I'm gonna text him and I say, hey George, I figured out the production problem and I can get you a solution in about a minute. I hope that's fast enough. So George Gonzola, who's my main contact there, he responds to me. He says, no, that's unacceptable. Please make faster. So I think what George is trying to tell me is that this does not solve the problem fast enough. He's not happy with this. He really wants something that solves faster. So I say, okay, George, I'll see what I can do. So I'm going to go back and I'm going to see what I can do to formulate the problem differently and try to solve a different model and see if I can solve it faster. So the first way that I'm going to try to do this is to formulate the problem using tuples. So this is a common way of doing things. Instead of using an array where we have a number of binary variables that are either 0 or 1 if we're producing that cheese at each time period, what we're going to do is we're going to keep track of for each cheese what our start time is and what our end time is, and also which production line it is on. So in this case, our production line actually has to be an integer variable. And here I have these decision variables S and E, which are our start time and end time. And here I have them as integers, but depending on your problem application, you might be able to even make these real numbers. So you can make them continuous decision variables, which is faster than having integer decision variables. But here, for the case of this sample, I'm gonna have them be integers. So we have these tuples of integer variables for our start time, end time, and our production line. We're also gonna keep track of our variable R, which is gonna keep track of if two cheeses or if we're gonna compare their start times. So that variable R with the index of C1 and C2 is gonna be 1 if cheese C1 is produced before cheese C2. And we are gonna have another decision variable M, which is also indexed for each combination pair of cheeses. That's gonna keep track of whether two cheeses are on the same line. So if cheese 1 and cheese 2 are on the same line, then that corresponding element is gonna be 1, otherwise it's 0. All right, so we're gonna try to formulate the problem this way with these tuples. And again, we're gonna minimize the last end time producing cheese. So here, this time, our decision variable, or our objective function variable is gonna be that E variable, decision variable. So we're minimizing the last possible time where we're producing cheese. This constraint, again, is gonna make sure that we're meeting the demand. So we are saying the end time minus the start time has to be as long, at least as long as the time we have to produce the cheese for in order to make enough of that cheese. This, again, is enforcing that constraint for those production starts. So you can analyze this, and all these slides and everything will be available later, but I'm using a big M constraint here, which is a common thing that we do in integer programming, right? So we create a parameter M, which is large enough to make sure that this right-hand side of that first constraint there is going to be 0, or it's going to be very small, one or the other. So we just make, this is our constraint to make sure that that R hat variable is either 0 or it's 1. It's a binary variable. So this is going to enforce that that R index on C1 and C2 is going to be 1 if and only if C1 production starts before C2. So this is a fun little constraint just to check comparison of start times, which is a common thing, again, that occurs in scheduling problems. And I'll show why we need this in a minute. We also have our variable M, which similarly, again, we're using big M constraints. So M is a large number that people usually choose to be around like 26. It really depends on your problem. If you know that there's an upper bound for what the limit could be, you can set it equal to that number. I would say the larger you set it, the more risk you take of having an ill-conditioned problem. So, you know, there is lots of literature on how to choose this number. But anyway, we are choosing this M variable or setting this M variable so that for every cheese1 and cheese2 index, that M variable is going to be 1 if and only if cheese1 and cheese2 are produced on the same line. So we're going to keep track of those comparisons of different production lines. And we're going to use M and R in this last constraint that is going to make sure that only one cheese is being produced on a line at a time. So if that M variable for cheese1 and cheese2, if M is equal to 1 and R is equal to 1, which means that their minimum is equal to 1, then we want to enforce the constraint that cheese2 starts after cheese1 ends, right? So that's how we're going to formulate making sure that each cheese is produced on one line at a time. So this time we're saying we're comparing those start times and end times. So if cheese1 starts production before cheese2, then we have to start cheese2 production after cheese1 finishes. Okay, so this is our tuple formulation. So I'm thinking this might be faster, but I really want to try a few different things. You know, the cheesemake factory is very demanding. So I want to see if there's something else I can try to make this faster. So not only am I going to formulate the problem differently, I'm also going to implement a warm start. So for those of you who may not be familiar with a warm start, this is a common concept in optimization. And the idea is that an optimization solver finds a feasible point, and then it tries to make that feasible point optimal in very general terms. But if we can feed the optimization solver an initial point that is feasible to start with, then it can start from that initial point that we call a warm start. You can feed it that warm start, and then it can try to make that point optimal. This usually makes the optimization solver much faster. This is a huge thing, right? A lot of times, especially with integer programs, finding the first feasible point is one of the hardest parts. So if you can give the solver an initial feasible point, that is always faster than just having it, you know, have a cold start. So no initial point. Even if you start from a bad solution, even if that feasible point is terrible, it doesn't matter. It's going to be faster than not giving it a warm start. So I'm going to try to give this a warm start and see how that goes. So for our problem here on the left, I have some pseudocode for what I did to create a warm start. But basically what I did is I just iterated through the cheeses and say assign cheese 1 to production line 1 at time 1, and cheese 2, production line 2, and iterated through and kind of stacked the cheeses productions on top of each other, just looping through the system, finding a feasible solution of how we can produce these cheeses on these lines. So this depends on your problem. Oftentimes it is actually difficult to think of a feasible solution. If you could generate a feasible solution, then you might not be struggling to solve the optimization problem. So this coming up with a warm start, again, is something there's tons of literature on, but if there is a simple way to create a feasible solution and pass that to the solver, I would highly recommend doing that. Okay, so I solved this problem these two ways, and it turns out, which was unexpected for my sample problem in this size of problems, using tuples, even with a warm start, was not faster than arrays. So again, this was just for my problem, and that just does not mean that for your problem this will not work, because I will say that a lot of times this is faster. So that's why it's important to implement few different things and see what works for yours. But for this problem, using tuples, even with the warm start, was not faster than arrays. So as you can see, as the problem size grows, we're still increasing in time, but it really depends on the formulation and the data that we're passing it. So that's too bad, because I really wanted to be able to go back to the cheesemake factory and say that I solved your problem faster, I got you something that was much better, but I can't. So I'm gonna have to go back, and this time I'm thinking I'm gonna talk to someone else. So maybe George is just really harsh and not understanding, and maybe if I tell someone else, they'll understand, they'll say, yeah, that's fine, that will work. So this time I'm going to talk to Mac, and I say, hey Mac, I tried some other methods and I really haven't gotten the problem to solve in less than a minute. Do you think that's going to be okay? I'm hoping that George might be okay with that. And Mac and cheese. So Mac responds to me and he says, it might be okay, but we're going to have to ask Matt. And one more thing, I know you're obsessed with this whole optimality thing, but is there a way to find a solution that's close to optimal in less time? And I say, okay, Mac, I'll see what I can do. So Mac brings up a very good point. And this is a point that often really happens in real life, right? So you have an optimization model, and we are oftentimes so focused on finding the exact optimal solution. But if we can find something that's close to optimal in less time, oftentimes that is more than good enough, right? We just want to find something that is very, very good. So we're going to try to do that. And we're going to do that by using optimization-based heuristics. And there are a lot of different optimization-based heuristics that you can implement for your specific problem. I'm introducing two here. And I'll talk about how I can use them for a whole problem. But in general, I think these are ideas that you can kind of think about intuitively how you can apply them to your problem and how it would work with your set of constraints. So it really depends on what your formulation is. But the first one is pre-processing. So this one kind of just requires thinking intuitively about your problem and seeing if there are certain things that you think might reduce the search space. So you want to see if there's a way you can reduce the number of possible options that it's going to search. So for our problem, what I'm going to do to pre-process the data before I pass it to the optimization solver is I'm going to say, okay, well, we have 3 production lines and we have 10 cheeses. So why don't I take the 3 cheeses that have the longest production times and assign them to the 3 different production lines at time 1. So then if I set those 3 and we kind of pre-process and fix those as constraints, then I'm only going to have to optimize over 7 of the different cheeses, not 10. And that's going to reduce our search space. So the optimization solver is going to find a solution faster. So the most time consuming production is going to be on line 1, second most time consuming on time 2, and so on. And then what we're going to do is once we kind of fix those, we can add constraints to the model to fix those production lines. So that's the first way that we're going to pre-process. And the second way is with region splitting. So again, this is very dependent on your problem, but you can imagine if you have a really large problem, if there are any subsets of the data that you can split it into, so you can split the problem into subsets of data and solve those smaller problems and then aggregate it all together, you won't get the overall optimal solution, but you'll probably get something close. And if you have a problem that you split into 10 subproblems, then solving those 10 smaller problems and then aggregating it will be faster than solving a problem that's 10 times as big. So if we can split the problem into smaller pieces, put it back together, that will almost always be much faster than solving the larger problem. So for our problem, what we're going to do is we're going to solve P problems. So we're going to solve 1 problem for every production line. And for each production line, we're going to assign P divided by C, different cheeses to each of that. Or actually, no, that should be cheese C divided by P. Or the floor or the ceiling, whatever number gives you an integer. So for us, we're going to assign either 3 or 4 cheeses to each production line and then optimize over each line. So we're going to split it into the regions that way. So for our pre-processing formulation, all we're doing here is we are figuring out what those P longest cheeses are. So find the P cheeses that take the longest time to produce, get them in a set, and then we're going to add a constraint here on the bottom that sets that production line for that cheese to that line. So we're going to fix that constraint. And here I'm using the tuple formulation just because it's simpler to show this for that, but Obviously, you could also use this in the array formulation or any way you want. And for the region splitting, we're going to isolate each of the different production lines and solve the problem for each of the different lines. So for each line, we'll figure out what those, the C divided by P, whatever those number of cheeses is, and assign those to, assign that many cheeses to each production line. So we're going to make sure that we choose what those cheeses are, just assign those cheeses, and isolate each line and optimize over that. Intuitively, my guess is this will not do very well, but it will be much faster. So let's see what happens. All right, so these are the two methods, and we can compare them to what happens when we solve with arrays. So here, again, I have that WS, so I'm actually using a warm start here with the arrays, so it's a little bit faster than we had before. So if I use the warm start with the arrays, and then I solve that, and I compare that to what happens if we were to pre-process, and if we were to split by production line. So obviously, when we do the pre-processing or region splitting with these heuristic methods, we're not going to get something that's optimal, but we're going to get something that might be close to optimal. So you can see with the pre-processing, we solved the problem in 8 seconds, and we are 14% from optimal, which is still pretty good, I think. Whereas with the region splitting methods, where we're separating each production line individually, I could have guessed that that was not going to be very good, and it's not. So we're 34% from optimal, and that problem solves in a second. So how you want to kind of weigh the importance of these two things, of how far you are from optimal and how long the problem takes to solve, is really up to you, and depends on the specific application and what people are willing to be happy with. But in this problem, I think that 14% and 8 seconds is pretty darn good. So I'm going to go with that one. And I'm going to go back to the cheesemake factory and tell them. Okay, so this time I'm going to talk to Matt. And Matt is my favorite character in the cheesemake factory. I'm going to tell Matt, use some heuristic methods to speed up the process of finding a solution. And now the problem solves in 8 seconds, and we're within 15% of optimal. So Matt Zarella, who has kind of a creepy look to him, actually. So Matt says, it's great news. We're really happy with that time, but you're not taking into account turnover time. And the progressive laziness of the cheesemakers means that turnover time is quadratic in end time. I'll send you the info. Okay, Matt, I'll see what I can do. So I think what Matt is trying to tell me is that there is a turnover time in between cheeses. So if we are producing Gruyere on a certain line, and we're going to switch to producing Brie, then there's a turnover time in between producing the Gruyere and producing the Brie, right? And as time goes on, so as we progress throughout the day, the cheesemakers get lazier, so that amount of time it takes to turn over actually gets larger over time, exponentially grows. And it's quadratic. So we need to take those turnover times into account, and we're not now. So Matt sends me over the info, and turned out, as he said, turnover time is quadratic in end time. So as the end time increases, that amount it takes to turn over is going to increase quadratically with that end time. So this is a quadratic equation that we can plug into our constraints, and it is convex, which means that it works with the formulation of my model and my data. It's a positive semi-definite constraint, which Gurobi can solve. But there are other ways to do this as well. So the other thing that we can do is, instead of using the quadratic, we can use a piecewise linear approximation. So in this case, I'm going to take this quadratic function and I'm going to split it up into 3 pieces. And each of those pieces, I'm going to fit a linear piece to that. So I'm going to approximate this with these three linear pieces. And what we can do in the formulation then is we can have a binary variable. Here we're going to have 3 binary variables, one for each piecewise piece, and the sum of those variables is going to be 1. So we're going to say, here are the 3 options, pick one of them, and use that linear equation to describe this turnover time. So instead of using the quadratic, we're going to use the piecewise linear formulation, and I'll show how we can do that in a minute. So this is going to be our quadratic formulation. So we have a few more parameters here. We have our quadratic coefficients for each of the different pieces of the quadratic formula. And we also have our linear coefficient and the constant coefficient. And we need to take this into account in the amount of time. This is one way of doing it, right? We can say, well, you're not just meeting the demand, but you also have to account for that turnover time. So the amount of time we spend producing a cheese is going to be at least as big as the production time needed, plus this quadratic equation in terms of turnover, in terms of the end time. All right, so again, this is a convex equation, so we can solve this. But we can also formulate it as a piecewise linear formulation. So here we have another binary decision variable, W, that we're introducing. And N is our number of piecewise pieces. So for the example before, we had 3 of those. And we're going to have 3 of those for each of the different cheeses, because each of the different cheeses we're modeling, we need to pick which piece we're going to use. So we have those binary variables. And then we have our coefficients that describe each of the linear and constant coefficients, so the slope and intercept for each of those linear approximations. So here, we're going to say that the amount of time we spend producing each cheese is at least as big as the production time we need plus this linear equation in terms of end time. And that we're multiplying that by our binary W variable, and then we're making sure that those W variables sum to 1. So we're going to pick one of those pieces, and the optimization solver is going to pick the optimal piece, right? Which is why optimization is so cool. So we're going to pick one of those pieces, and then this will be described by the piecewise linear formulation. Okay, so if we solve this, we can see that as the problem gets larger, the piecewise linear formulation actually solves faster than the quadratic. So again, this is just in terms of my sample problem, but as I think at the beginning, the quadratic actually solves a little bit faster. You can't quite see it in this chart, but trust me, it solves a little bit faster with the quadratic when the problem is smaller. But as it gets bigger and we get more binary variables, piecewise linear is faster than the quadratic. So it's very interesting. So that means that we are going to use the piecewise linear formulation to solve the problem. And now we can solve it now in 30 seconds, which is a little bit longer than the cheesemake factory had agreed to before, but hopefully they're going to be okay with that. So this time I'm going to text the group, all of them, and I'm going to say, hey guys, I'm taking into account the turnover time now, and I'm still finding a solution in around 30 seconds. And luckily, they're happy with that. They all think it's great. They're happy with my solution. 30 seconds is sufficient for them, so I can throw a little party. I'm very excited that it's good enough for them. All right, so we found a solution to our problem. We tried all the different methods. We ended up having to change our formulation a little bit to take into account turnover time, but we still solved the problem, and we got something in reasonable time. Okay, so in summary, here are a few different things that you can try to apply to your problem. So again, every problem is different, and what is going to work for your problem may not be what worked for this sample problem. So it's always important to try a few different things. And the first thing that I generally try is trying different data structures. So if arrays of a lot of binary variables doesn't work, then you can try tuples with different start and end times. Dictionaries might not quite apply to decision variables, but dictionaries in Python are generally very fast. So if there is a way that you can use dictionaries in Python, it's definitely the way to go. So trying different data structures of the data, however that applies to your problem, is one of the main ways to try to model the problem differently. Using a warm start is very important. If there's any way you can generate a feasible solution and pass that to the optimization solver, then I would highly recommend that. That usually speeds things up quite a bit. Pre-processing the data and fixing the values that can be fixed. So for our problem, that was kind of assigning a few of the production lines and then optimizing over a smaller subset. You can either do that by keeping the same model and figuring out beforehand what data it is you want to fix and figuring out what those values are that you want to fix it to, and then adding those constraints to the model. So the model is still exactly the same. Or you can do something where you assign those values and then change your model a little bit and adjust it so that you are only solving for the smaller problem. I wouldn't always recommend that one. I think it's important to kind of keep the model exactly the same. So I usually just add a constraint to fix those values. You're still going to have a smaller search space because you're fixing some things, but it means you don't have to make a huge adjustment to the model, which sometimes, most of the time, can be a pain. The next thing is splitting up the problem by region. So again, we split up by production line, but if you can split up your problem into subsets, however you can do that and solve a few smaller problems, That's a big thing. You can even split the problem up by time. So usually in any type of scheduling problem, the time periods, what happens in one period is really dependent on what's happening in the other periods. So splitting things up by time does not always work. But if you say are trying to solve the problem for an entire week, if you can solve a day at a time and split it up that way, that works. There are also a few ways you can use a Lagrange relaxation methods to split things up by time and kind of combine it in the end. I would say that's more advanced than these advanced methods. But if you have any questions on that kind of stuff, feel free to reach out to me later, and we can always talk about that. But splitting things up into smaller subproblems, however you can do that, usually speeds things up quite a bit. And lastly, just a quick trick that I have found. Scheduling problems always have a lot of binary variables, right? And if you have a large number of binary variables that all need to be 0, you can either have a constraint for each of those that sets each of those decision variables equal to 0, or you can set their sum equal to 0. And I have found that in practice, if you set their sum equal to 0, that is oftentimes much faster than individual constraints setting them all to 0. So it really depends on your problem, but if there's a way that you can do that, use the sum instead of the individual constraints. I have found it to speed things up quite a bit. And lastly, just some best practices. These are things that I have learned the hard way in implementing a lot of optimization models, and I'm sure that a lot of you have found these to be very relevant as well. But just reminders for those of you who maybe haven't learned the hard way yet. The first thing is just writing generic code, which is something that applies to any kind of code or any kind of program you're writing, right? You want to make things as general as possible. And especially with these optimization models, writing the code in a way that can take in any data in the correct format and solve that problem regardless of the size or what the exact numbers and parameters are. So just take in any model, have your model take that in, read it in, pass it to Gurobi. Will save so much time in the long run. And it's, best practice is always the way to go. Especially with things like this, though, I have found with, for example, when I was, writing the code for this sample problem, I had, all my models took in the same format of data, right? So I had a lot of the code was the same. It was shared code, and then I just added a few things to it and solved the different models. But it made it much easier to try all the different options if I had one format and everything took in the same format and I could solve the model based on that. The second thing is creating a smaller data set that can be solved very quickly. So this is an important one, again, that I have learned the hard way. Sometimes I think it will take me a while to create a small data set. It's not worth it. I have the real data, but it is always worth it to create a smaller data set and try to solve the problem on a smaller data set and compare that before you apply to the big problem. A lot of these problems take a few hours to solve. So if you have to rerun something that takes a few hours every time, that's going to make your life very difficult, right? It will take you a very long time to figure out the fastest way to do it because every time you run it, it's a few hours. I found that if something takes more than 15 seconds, then I usually go and I start doing something else. And then they come back an hour later and I'm like, oh yeah, I forgot I was doing this thing, right? So getting something that solves in a few seconds as fast as possible so that you don't get distracted, you don't end up going and doing something else. You create that smaller data set and test it on that as much as possible. And then lastly, of course, trying a few possible formulations. So try anything you can. Whatever applies to your problem, however you can split it up, however you can pre-process the data or different formulations, try whatever you can because you never know what's gonna work well for your specific problem. Okay.